A vision system looks at a stop sign. A few altered pixels, imperceptible to humans, cause the network to confidently classify it as a speed limit. The machine is highly capable, yet it fails in ways we cannot interpret. In computer science, we refer to a model's raw predictive power as its instrumentality. It is the metric of accuracy, how reliably a model executes a specific task, whether that is labeling an image or steering a vehicle. The opposing concept is intelligibility. This is our human capacity to look beneath the surface and trace the exact logical chain the machine took to reach its decision. Modern deep learning architectures heavily favor instrumentality. They process vast amounts of data through millions of hidden weights to optimize their predictions, but the system provides the final answer without revealing the reasoning behind it. In high-stakes environments like medicine or law, a highly accurate guess is insufficient on its own. A lawyer requires a chronological story to assess liability. A doctor must verify the logic before prescribing a treatment. Without a coherent narrative, trust breaks down. This tension between raw performance and transparent reasoning is a recurring cycle. It traces back to early computing projects that relied entirely on brute force calculation. While calculating millions of potential variations works efficiently within the rigid constraints of a chessboard, that brute force approach collapsed when researchers applied it to the ambiguous, highly variable domains of organic chemistry or patient healthcare. That failure led to a distinct era in the 1970s and 1980s known as symbolic AI. Researchers discarded brute force computation, replacing it with systems designed to execute explicit, step-by-step logical deductions. To solve today's explainability crisis, modern engineers are looking backward. They are examining the precise engineering choices made during this era to see how earlier developers successfully mapped human logic into machine code. They are finding that explainability cannot be patched onto a finished model. It dictates how you build the software from the ground up. Early computing initiatives in the 1960s attempted to build general problem solvers, universal deductive algorithms designed to tackle any challenge. Those broad algorithms failed to produce meaningful results in specialized fields. The field responded by narrowing its focus. Instead of trying to build a universal thinker, researchers began intensely studying individual professionals, mapping the highly localized, inductive reasoning of specific experts solving specific problems. Observing this shift, computer scientist Edward Feigenbaum formulated the knowledge is power hypothesis. His conclusion was that a program's predictive capability is driven almost entirely by the volume and quality of the specialized heuristics it holds. The elegance of its core reasoning algorithm is secondary. This insight birthed the practice of knowledge engineering. Developers sat down with doctors, chemists, and geologists, painstakingly extracting their mental rules of thumb and formalizing those specific conditions into executable code. The process proved that professional expertise relies heavily on the accumulation of highly organized, explicit domain data. This chart illustrates the architecture of an expert system. Notice it is physically split into two distinct areas, a knowledge base and an inference engine. The knowledge base is an isolated repository. It exclusively stores explicit domain facts alongside rigid production rules formatted as simple if-then nodes. The inference engine contains the operational logic. It evaluates user inputs, searches the knowledge base, and triggers specific sequences of those I-then nodes to output a final diagnosis. Because of this physical separation, the system has a native reverse run capability. If asked to explain its reasoning, the engine simply prints the exact chronological sequence of the rules it triggered. By decoupling the raw data from the operational reasoning, the architecture natively guarantees transparency. The system is fully accountable by design. Building these systems revealed a harsh operational limit, known as the knowledge acquisition bottleneck. Manually extracting, formatting, and hard-coding every possible heuristic from a human expert demands an unsustainable amount of time and capital. More critically, it introduced a fatal flaw called brittleness. A rigid rule-based system lacks broad contextual common sense, causing it to fail catastrophically the moment it encounters data slightly outside its explicit programming. If a medical expert system receives a patient's age and weight data that was accidentally transposed by a clerk, it will not recognize the typo. It will confidently prescribe a potentially lethal dosage of medication based strictly on the rules it was given. To survive the noisy, unpredictable nature of real-world data, the industry pivoted in the 1990s. Researchers abandoned strict rule sets in favor of statistical and probabilistic models. Instead of coding absolute logical certainties, engineers built Bayesian networks. Nodes were no longer connected by strict if-then rules, but by dynamic percentage probabilities. The AI industry traded away strict, explainable logic. A flexible, probabilistic guess proved far more useful than a brittle system that breaks entirely when faced with unexpected inputs. The triumphs of probabilistic models led directly to today's data-heavy deep learning architectures. We deploy hyper-complex networks that process vast environmental inputs with incredible accuracy, maximizing instrumentality, but returning us to the black box crisis. This chart shows a performance metric, or area under curve, for a medical classifier built in a high-dimensional space. According to MIT's Randall Davis, when engineers apply explicit mathematical constraints to make this black box model transparent, its accuracy drops from 0.90 to 0.85. This illustrates a strict constraint in machine learning architecture. You cannot maximize both raw performance and human explainability simultaneously. To navigate this, researchers are exploring engineering compromises like generalized additive models. These architectures force explicit human-centric categories back onto statistical classifiers, breaking down complex decisions into smaller, observable functions. Advancing AI into critical sectors requires resurrecting the expert system zeitgeist. Engineers must intentionally sacrifice a marginal degree of raw performance to regain the indispensable power of human trust.